Welcome back. So, today we will go through the thermal design of battery pack. A part of that we have started in the last class, where we have talked about why thermal design of what are the things needed in thermal design of battery pack, why thermal management is important, and we have discussed several things, and especially about temperature. That temperature impacts the pack directly. What are the things? Electrochemical reactions within the cell, that is getting impacted by the temperature. At a very low temperature, this electrochemical reaction rate is very slow. So, we do not want very low temperature. At very high temperature, it tend to cell tend to degrade, as well as there could be several other problems associated with that, like thermal runaway, failure of components and all those. It also decreases if you do not maintain the temperature in the proper range. It also decreases the efficiency of the pack, charge acceptance, power energy availability, safety and reliability, life and life cycle costs. So, these all the things depends upon the proper temperature or proper temperature range. What are the required function of thermal design? That also we have gone through: the compactness, lightweightness, easily packageable, reliable, serviceable, low cost, low parasitic losses, and the optimum temperature ranges. That is a required function of a thermal management system or a thermal design. It should also have the small temperature variation among the cell to cell or within the pack. So, temperature gradient, we say that should be very low. And then we have also discussed that what should be the optimum temperature range for the operation of the pack. So, for the current cells, for current NMC cells or other varieties of cells, the temperature range is something between 15 degree to 35 degrees C. So, if a temperature is in between that, you can get based out of the its life, calendar life as well as cycle life, and it will perform well. And then we also mitigate different type of accident which can happen. One of them is thermal runaway, other things like melting of materials or electrodes here and there. So, then we have divided that there are basically three temperature range: normal, like moderate, high temperature and low temperature. At high temperature, what are the things required? Mostly you require cooling at that time. At low temperature, you require heating. At moderate temperature, like 15 to 35 degrees. So, in that case, only just whatever the heat is getting generated, that you have to remove, so that the temperature should not elevate. Then we have also talked how heat is generated in a battery pack. So, the simplest form of the heat generation, which can be written in mathematical form, is in joule, like joule heating is nothing but I square R. So, I square is the current drawn from the battery or current fed into the battery during the charging, current drawn from the battery during the discharge, and the internal resistance of the cell. Basically, this will allow us to estimate the heat load or heat generation in the battery. And how does it impact? Then its cell, wherever the current is flowing. In cell, we are taking the current out or putting the current back inside. Then bus bar, current flows through that one, and in the BMS. So, these three things are basically a major source of heat generation inside a battery pack. Now, this heat generation rate can be impacted by several things like DOD, temperature of bus bar, temperature of cells, because the internal resistance is also a function of temperature, DOD as well as OCV. Then we have started an example problem how to estimate the heat generation or heat loss or heat load. These all are similar terminologies. So, what there we have done, that we have considered a same pack what we have developed during the mechanical design 2P16S with the cell capacity of 15 Ah. The internal resistance of that cell is 10 milliohm, or internal impedance is the 10 milliohm. 10 milliohm is generally resistance is at higher side, and this you achieve during the end of the life of the battery pack. That means when the it has been degraded to 70% of its original capacity or 75%. So, whatever we put is approximately it comes at that. However, for a new cells it would be something like between a fraction of milliohm to 5 milliohm. However, when you are doing a thermal design, it is not only about that particular moment or only for new cells. It has to take care of the complete life cycle of the cell also. That means, at the end of the life cycle, what would be the heat generated, that you have to anticipate in early design, and then you have to design your thermal management system with that. So, generally it becomes twice at the end of life cycle of a cell, the internal resistance become twice. So, for a new cell it is a 5 milliohm. However, for estimating the things at the end of life, we have taken it at 10 milliohm. Now, the module is being discharged from 100% to 20% SOC. The battery pack is discharged from 100% SOC to 20% SOC, and then at the rate of 1C discharge. 1C discharge means if it is 2P, then it would be 30 ampere. So, what we have to do? We have to calculate the heat generated and energy expelled by the module and compare energy lost as heat to total module energy. So, we are discharging, that means we are doing some useful work, like by either by driving motors or something. So, there are some useful work, but there is some energy getting lost as a heat, that is not a useful, but still first of all that gets generated because of the internal resistance. At the same time we have to also remove. So, we may end up adding some extra energy for removing that one, means we may be consuming some extra energy to remove that one. So, first, even before removing, first we need to know what would be the estimate, what would be the amount of energy which we need to remove, that is as a form of heat. So, that is what we have done in this example problem. So, if you see the cell current at 1C, for one cell it is 15 ampere only, 2 cells together gives 15 ampere plus 15 ampere 30 ampere, 2 parallel. So, for one cell it is 15 ampere. Now, cell internal resistance is 10 milliohm. So, heat generation for each cell would be 15 square into 10 into 10 to the power minus 3 watt. So, that is 2.25 watt. Now, heat generated by the pack, how many cells we have in the pack? 2P16S, that means 32 cells we have in the pack, and each cell is generating a heat of 2.25 watt. So, what would be the total heat generated by the pack, or you can say heat load of the pack? This is only because of the internal resistance, is 72 watt. So, energy lost by the pack as a heat, since it is coming from 100% SOC to 20%, consider linear behavior here. SOC is, however, you would have seen in the last chapter 4 that it is not as a linear function. SOC is not a linear function of OCV or discharge. However, consider here as a linear function just to simplify the problem. So, the total time taken 100 to 20% means 80% of the time is 2880 seconds. Heat energy lost becomes 6.48 kilojoule. The heat lost by the pack, this is for one cell, multiply with 32, you will get 207.36 kilojoule. However, the total energy from 100% to 20% SOC, that is around 5045.76 kilojoule. So, what is the ratio of heat to the total energy? Is that comes around 4.1%. 4.1% is a huge energy. If we can save energy, my range will go by 4%. Sorry, approximately 5%. And 5% range for 100 kilometer battery pack, it's a 5 kilometer, it's a huge. Now, we already know this much heat is being generated, 72 watts as a power, or if you talk about energy, it's a 207.36 kilojoule. So, first of all, it has generated. Now, someone has to remove that heat. If it is not removed, what will happen? The temperature will keep on rising. So, now the extra energy will be taken from the battery to remove this heat, because you cannot simply remove it. You have to use some mechanism, either active or passive. So, those mechanisms we have to use. Also, you see here, we have not considered the environmental impact here. Environmental impact means, now if we want to maintain between 15 to 35 and my environmental condition is 45 or 48 degrees centigrade, what will happen? There is a possibility that some heat will go inside. If you are not taking out heat, so that heat will get added up. So, the heat load is not only for the battery pack. If there is any heat coming from outside, or if there is any heat going to outside, will also be considered for the total heat load calculation, and then we have to remove that heat. If there is a temperature difference, it is impossible to not have a heat flow. You can reduce by putting some proper insulation material and all those things, but it cannot be zero. It can be reduced. We will talk those things later part of the class. So, what we see here, for a SOC from 100% to 20%, 4.1% of energy is getting lost because of the heat generation. And why that heat is getting generated? Because of the internal resistance. How can we reduce the heat loss? What is the heat loss here? It's I square R. I is the current, and that we also say C rate. If we reduce the C rate by half, let us suppose 0.5 C, what will happen? Our heat loss would be reduced by 1/4, because it is a function of I square. R remains same, we cannot change R because it is the property of the cell, but I we can always control. So, we make a battery pack for lower charge or discharge, our heat generation would be less. So, we will lose much less energy. So, in that case I can say, if I can reduce the heat load by current drawn or during the discharge, and current put during the charging by half, by let us suppose 0.5 C, this energy loss, which is right now 4.1%, will go down to approximately 1%, just by changing the C rate by half. Secondly, we can select a cell which have further lower impedance or further lower resistance. There are cells available which has an impedance of 1 milli. At the end of life cycle, it may go to 2.5 milliohm, but still it is 1/4 times of that one. However, the impact of the resistance is a linear. However, impact of current is square. Let us move to the next slide. After understanding how the heat is getting generated, we will try to understand quickly the first principle of energy flow. Heat is a form of energy. Heat will flow only when if there is a temperature gradient. Generally, we say it is a zeroth law of thermodynamics. Heat will flow only when if there is a temperature gradient. The similar way in electrical current, unless you do not have a potential difference, you cannot flow the current. There will not be any current. So, for heat to flow, the temperature gradient is must. Depending upon the temperature gradient, how much heat will flow can be defined. So, it has basically three modes: conduction, convection and radiation. In the simple form, conduction we represent the heat transfer due to conduction we represent by Ka delta T, where delta T is the temperature gradient. And conduction generally happens when there is a continuous medium like solid. Even in fluid, even in liquid it happens. So, the temperature gradient within same body. Now, there is another mode is known as convection. A lot of researcher or expert, they said there is no mode like convection. It is a combination of conduction. It is extended part of conduction. Will not go to that. The convection is by bulk. Convection heat transfer happens because of the bulk motion of the fluid, the temperature gradient and bulk motion of the fluid. So, here the convection heat transfer is because of two material. The temperature gradient which comes is because of the two different things. One might be solid or liquid or something, other would always be a fluid. Fluid means either liquid or gas. So, how do we define that? The Q convection is nothing but HA delta T, where H is the convective heat transfer coefficient. A again is the cross sectional area, and delta T is the ambient and that particular object temperature. Okay. And then radiation is slightly different. However, we will try to put back in that form, because radiation heat transfer is proportional to T to the power 4, temperature to the power 4. So, the simple explanation we have put Q radiation epsilon sigma A T to the power 4 surface and T to the minus T to the power 4 infinity, T infinity to the power 4 and T surface infinity, T surface to the power 4. Now, if we want to convert into like HA delta T or Ka delta T, to simplify that one, so we can put here H radiation into A Ts minus T infinity. How that has come? Now, you A square minus B square is nothing but A plus B, A minus B. So, similar way you can put T square, Ts square whole square minus T infinity square then whole square. So, that will become Ts square plus T infinity square and then into Ts square minus T infinity square, and then again you further make it Ts minus T infinity into Ts plus T infinity. So, now you have three terms. So, Ts minus T infinity you take out, rest of the term you put it back into the H form. So, it is just to convert in the similar form Q equal to Ka delta T or Ha delta T. So, that is how we have done here. Now, it is similar to what we talk about in conduction and radiation. Okay. Now, so the next what we are going to define is thermal resistance. So, thermal resistance is nothing but for conduction it becomes 1 by Ka, for convection it becomes 1 by Ha, and for radiation again it becomes 1 by H radiation into A, and which is equal to H radiation is equal to epsilon sigma Ts square plus T infinity square multiplied with Ts plus T infinity. See, here you have Ts to the power 4.
To the power 4 there.
Yeah. So, what you see, the question is that why this additional term of Ts plus T infinity come.
Right.
So, here we have T to the power 4, Ts to the power 4 minus. So, Ts square, this will become Ts square whole square minus T infinity square whole square. This will get converted into Ts square plus T infinity square into Ts square minus T infinity square. Now, this term is here. Now, this term get converted into Ts minus T infinity. Now, this is nothing but for us it is delta T and into Ts plus T infinity. So, this term has come here. And for HA, this H radiation, this term has come. So, the for conduction what would be then it becomes what the thermal resistance? So, 1 by K. For convection it becomes 1 by HA, and for radiation again 1 by H radiation A, where H radiation is sigma epsilon Ts square plus T infinity square multiplied by Ts plus T infinity. And then Ts minus T infinity, again we can say always delta T. So, how do you compare with a heat flow and electric current flow? Similar way, for heat flow you need to have two temperatures, two different temperatures, and there would be a heat flow, and you can say Q equal to nothing but delta T by R. R is nothing but thermal resistance. It could be conduction, it could be convection, or it could be radiation. For electric flow, I is nothing but delta V by R. So, again you should have two differential. So, this two gets correlated, means the similar forms, similar equations. Here the delta T, there it is delta V, and denominator is resistance. So, here it is thermal resistance, in that case it is electrical resistance. And to make the thermal resistance to have the similar formation, it was easy for conduction and convection. However, it was difficult for radiation, but we have managed to bring the form of R resistance in the same form of conduction and convection. So, the conduction basically within one object, either solid or liquid generally. Convection generally happens between two objects. One could be generally one would be either solid or liquid, and the second medium would be either liquid or gases. So, we say it fluid. And the radiation does not need any medium. It can happen. Now, I am radiating to you, you are radiating to me. So, net, because of the temperature differential, that whatever the transfer net heat transfer is happening, that could increase the temperature of this room or can decrease. Even I am radiating to the wall, wall is radiating to me. So, the radiation is always present. However, at a smaller temperature, lower temperature difference, it is not very significant.